Okay, now, so at least we have a better hold on what multiplication is. Nothing but repeated addition in this sense. Now, of course, this introducing multiplication is nothing but a segue to re-express this. I'm adding 10 to itself 10 times. Therefore, in terms of multiplication, what do I have? 10 times 10 is 100. This is the statement that 10, 100 is 1,000. Now that's the basis of. Oh, sorry.
Careless.
Penmanship. Of course, you like one go on, you know exactly the same time. 10 times 1,000 is 10,000, and so on. So that's the reason. So now to go back to our original problem, we have to do something a little bit more. And this is now a natural. Let's see what. Let me go on for 10 more minutes. There are two things I want to do. Let me do. Okay, let's do one thing at a time, of course. Let me go immediately into the following. So with your now addition, your multiplication. One of these concepts I want to briefly talk about. We'll come back to this again tomorrow morning. But right now, we want to use your favorite words in mathematics classes: associative property, commutative property, distributive property. You love those words, right? You're not telling the truth, you know. But to us, these are very serious things. Use it. So what I want to say is that both operations are associative, and they're both commutative. What does that mean? To say that addition is associative means what? So, addition, to say addition is associative, meaning it obeys the associative law, means that M plus N is of plus M and P the same as M plus N P for all whole numbers M and P. So with this morning we talked about, what we're going to do. We'll just do exactly the syllabus in the schools. But as I mentioned, we're talking as adults. Then there are certain tolerance that children probably don't have for symbols. And so what, instead of saying, keep giving you examples, I just say, you get used to this statement in symbolic language, which is, no matter what N and P may be, any whole numbers, you add N to P first, and then add N. Right? It's the same as adding N to N first, and then P. Okay. Now, of course, what you have to convince yourself about this is take a lot of numbers, try it out. By the way, this is quite spectacular, by the way. Do you appreciate it? Do you take this for granted? You should. Well, give me two numbers. Give me three numbers. Well, what is it? 5.
6.
Give me something big.
28. So 13.
I'm saying, right? This is the right time. I'm saying this same as 5 plus 6 plus 28. Now look, forget about the right. What's the left? The left is what? That's 11 plus 28, right? That's the left. What's the right side? Now forget the left. This is 5 plus 34. Compare these. Do you think they look obviously the same? Is that what you think? Oh, this is very non-trivial. So you're so used to it, you say, yeah. But it's not anything but obvious. These things say something very, very serious. Okay? So I have more to say about this in a minute. So that's associative law. Now, so what you will do, as I said, is to get lots of numbers and then try it out, and each time, spectacularly enough, they come out the same. And you're sold on it. That's good. That's good beginning. But ultimately, that's not very good. Because you're like this is you see that come out the same, right? 39 and 39. But then why should they come out the same? So we have to do a little bit more, do a more convincing argument. So what we can do is back to number line.
Yeah, exactly.
What does addition in terms of number line mean? Addition in terms of number line. Okay, so let's look at. Okay. 0, 7, right? You 7. You count to 7. That's so this is 7 steps, right? And then 7 steps again, right?
14.
Then 7 steps again.
21.
7 steps again. Right? Oh, I don't want to do that. One minute. Sorry. Sorry. That's not what I'm going to do. I don't want to go to here. I'm not doing multiplication. I'm doing addition, right? So that's all. 5 plus 4.
5.
That's all. 5.
I'm just wondering why you limit it to whole numbers.
No, because I made a mistake. Oh, what's that? I'm sorry.
Why do you limit the all whole numbers instead of
What do we know right now?
Oh, because that's all our working with.
Well, that's all you know, right? Now, we started from the rock bottom. Start from the beginning. We slowly build up. Now, that's another characteristic I want you to remember. You always start from the bottom. So you get step by step. But don't skip. They talk about skip counting, but don't skip learn. Skip count. Okay. So what you have got is all you can use. That's the main feature of mathematics. Okay. So that's 5 plus 4. Okay, so what it is okay. 1, 2, 3, 4, 5, 6, 7, 8. Oh, 8, 9, 10. So 5 plus 4, we say we start from 5 and 4 steps, right? So what it is that you start with 5. Now we think of 5 and a whole segment of this length. That's 5. 4 steps more, that means you get at a segment of how long? 4 units, right? 4 steps. So addition is the total length. Of these two segments combined in that particular way. No, but you don't want to say that all the time. Those two segments combined in that particular way, and then you draw a picture. So after a while, you get tired of this, and you just invent a name, and to indicate what was being done. And the name is concatenated. Concatenating two segments means join the two segments end to end, put them on a straight line. In other words, don't do this. Put them on the same straight line. Then you have a set on a segment and they find the total length. So from this point of view, so you have a geometric picture of addition. Now this is important. The fact that addition for whole numbers can be represented geometrically as just concatenation. Okay? So in general, m plus n, right? So in general, m plus n. Is the total length of the concatenated segments one of length m and the other of length n. So you have geometric representation. But now I can explain to you in one glance, in one stroke, why this is true. Okay? Because what does it say? Let's say, am I too fast? Does it follow?
Yeah.
So what it is that I have a segment of length m and p. The left-hand side is what? I look at this first. You've got that length. Then m plus that means what? You look at this and this put together. Well, then you have this length, right? So that the left-hand side is nothing but put this together first, and then put together with the first one. That's n plus p. So that's n plus p first, then n added to them. But what about the second one? Second one is what? You concatenate the two left segments first, right? n plus n and then plus p means what? n plus n is the concatenation of the first two segments. So that's this one. Done that, you add it to the one of length p, which means now you concatenate that. Well, you do that, what do you get? You get exactly the same segment. So that's no surprise. It should be associative. Now, to say that yeah, let's stick with addition because that's a simpler concept. We say that that's what we mean by associative, right? But the commutative, to say addition is commutative means what? Means that that n plus n is equal to n plus m for any whole number, right? That's the meaning of commutative. You know that, right? Now, again, initially you just try different numbers and keep counting. Right? 4 plus 5 is counting 4 steps beyond 5. 5 plus 4 is 4 steps beyond. You know, do all that, and then you check that it's actually always true. But again, in terms of the geometric representation, this is a no-brainer, right? And oh, that's a minute. But if you reverse the order, that would be n plus n. Are they the same thing? Well, obviously. Turn it around, right? Now this, of course, by no means that's the reason you want to use number line. This is a sort of very, very simple manifestation of the usefulness. So for addition, that's true. Now for multiplication, it's actually a little bit more difficult. And I'll just describe it. I have to describe it for a very good reason, because the geometric representation of multiplication is actually important when it comes to fractions. So what is for multiplication? What do you mean to multiply? 5 plus 4. No, you know it's 4 plus 4 plus 4 plus 4 plus 4, 5 times. Yeah, that's true, that's true. But it's not particularly revealing. There's a much more revealing picture of this. Well, let me give you a preliminary version. You are doing repeated addition. So it's 5 copies of 4. So you think of it as using dots, 1 copy of 4, right? 2 copies of 4, 3 copies of 4, 4 copies of 4, 5 copies of 4. So obviously, 5 times 4 is the totality of all the dots. 4 times 5 is what? Well, of course.
4 copies of 5?
5 dots, right? And then 4 rows of 5 dots. But I save myself the trouble of doing it because why? Yeah, this is looking at this way, right? This is looking at this way. 4 rows of 5s. So commutativity is, again, no-brainer in this. Right? Now that's good. That's good beginning. But this is still what we call discrete version, because this depends on 5 has to be 5 whole things. If you come to fractions, it's not going to be very good. But it's slightly modified, and it becomes very, very fantastically more flexible model. Meaning what? Think of unit squares.
Yeah,
1, 1, 1. So these are all unit squares. 1, 1. So you have 5 rows of the 4 unit squares, right? Now look at this, you have a rectangle now. One side of the rectangle becomes what?
5.
5. This is 4. Now you are now counting some totality of 5 rows of 4 unit squares, right? Well, we have a name for something like that. 5 rows of 4 unit squares lumped together. What do we call that? That's the area of 20 unit squares.
Right.
Or 20, square units.
Square units. Right.
Right? So 5 times 4 is geometrically interpreted as the area of rectangle of 5 by 4, so of sides. Side length 5 by 4. Side length 5 by 4. So multiplication becomes an area. Now there's a long historical background to this. You know the origin of a lot of for a long time, the Bible in mathematics is something called the element by Euclid. You all know of Euclid. In Berkeley, we have a Euclid Avenue, so everybody knows who Euclid is. By the way, only in a university town you have a street named after Euclid. Can you imagine it? Anyway, in Euclid, there's no concept of multiplication. Euclid does not talk about multiplying numbers. Euclid only talks about one thing, areas of rectangles. If Euclid wants you to understand what 5 times 4 is, it says, take a rectangle, one side is 5, the other side is 4. And leave it at that. So of course, that's the basis of most of mathematics after Euclid concerning what multiplication means. This has some limitations because now you multiply, instead of 2 numbers, multiply 3 numbers, what do you get then? Volume, right? Because then you can imagine 5, if you get 5 times 4 plus 3, then you have to stack that many unit cubes, right? 3 layers high.
Right.
And you say, what's the total volume? Right. That's great, except now, how do you multiply 4 numbers? The ancients couldn't imagine there's anything more than 3 dimensions. Therefore, they never multiplied more than 3 numbers. Which, of course, is very difficult, right? You can't do much mathematics by limiting yourself to multiplying only 2 numbers. And so mathematics was obstructed. The progress of algebra was basically non-existent for that reason. When you were not free to multiply numbers, there isn't much mathematics you can do. So it was at around 1600 that we finally came to terms with what multiplication is. Yes, on the one hand, multiplication does mean area and volume. On the other hand, multiplication has its own existence. It's purely number theoretical statement. 5 times 4 is 20. I don't care what 20 is. 5 times 4 is 20 because 4, So that's it. You don't ask for too much interpretation. So after that, then algebraic computations became possible. But so far as we are concerned, the commutativity of multiplication is a no-brainer because of this. Looking at look at this rectangle. This way, it's 5 rows of 4 rectangles. Right? Looking at this way is 4 rows of 5 rectangles, which is then 4 times 5. So there's the same area, two rectangles. So because you move it around, just rotate 90 degrees, makes it different. So that's commutativity. But associativity is going to be harder to picture. You have to draw something and say, it's the same solid, but look at it differently and so on. Now I won't bother you with that, but it's so hard to draw that. I used to have that picture in my field. But you get the idea. It's roughly the same. So multiplication is also associative. Which means m times n times p is equal to m times n times p for all whole numbers n and p. Right? Now, sometimes when I say something that's really you have to listen to me word for word, literally, and I will really tell you. But this is not one of those times. I tell you these names because you have to know it. It's talked about. And I even define for you what it means. When we say commutative means this, associative means that, associative or multiplication means that, commutative means n times n. Yeah, you should know such things. But in terms of, I mean, if your students grow up and want to be mathematicians, they will have to look at those very hard, these equations. Right? But for most of us, that's not really that important. The importance of these concepts is the upshot. The fact that, let's look at addition first. What is the effect? The net effect, knowing that addition is commutative and associative. Oh, you want it? Yeah, that's okay. Just get it.
Oh, maybe it's just right?
Maybe 10 minutes.
Okay, 10 minutes extra. Okay. Yeah.
Oh, I know. The net effect is.